in this case as some kind of flow of excitations. By flow, I really mean that at every point here, there's charge conservation, modulo d, I need to add that. And so if you believe me that so far, that you can think of any error configuration as a flow of excitations, then the only thing we need to do is you can apply the Helmholtz-Hodge decomposition, which essentially just tells you that any flow could be decomposed into a rotational and an irrotational part, which in this very simple case, it's really simple. You just have one loop, the rotational part, and then one string, the irrotational part. In a general setting, it could be a bit more complicated than that, but since rotational and irrotational means exactly that, you will end up with loops and tree structures independently. And then if you think about this a little bit more, you can easily convince yourself that for both the loops and the trees independently, the energy barrier, the energy required to construct them is at maximum 2. So this is for loops and trees, but of course we want the energy barrier for the whole model, for the whole Abelian quantum double model. So we have to maximize everything we have so far, and well, the maximum of 2 and 2 is still 2. So the energy barrier of the whole model is still a constant. So what that means for us is that because the energy barrier doesn't scale with system size, you will have a very small upper bound for the mixing time that doesn't allow for self-correction of these models. So with that, I will move on to some steps of the proof. So as I mentioned, we thought about the thermalization of these models. So the way we thought about this is we looked at this Abelian, which has a spectral gap of lambda. And so if you have a state rho 0, it's evolved by the Abelian, and you might be interested in how close is that to a state sigma, then this relationship is upper bounded by something that's exponentially decaying with time. So if your sigma here is the Gibbs state, the thermal state, then you can arrive to the following formula, which is essentially tells you that the mixing time goes as or upper bounded by something which is n over lambda in our case. So if you have this, then you can see the only thing we have to do then is lower bound the spectral gap. If we have a lower bound for the gap, then at the same time we have an upper bound for the mixing time. So that's what we did, and we used the Poincare inequality for that. This is actually not the inequality part, but we'll be getting there. So the spectral gap is the minimum of these two quadratic forms here, called the Dirichlet form and the variance. These are both related to the Abelian. You can actually think of them as the Dirichlet form as some kind of expectation value, and the variance is a variance. So the point is that these are well-defined forms, and you can get your spectral gap by dividing these. But also you can realize that if you want to find lambda here, as long as you find any mu that lower bounds this ratio for all f, this will also be a lower bound for the spectral gap lambda. So the only thing then you have to do is find such a mu and then maximize that mu, which is equivalent to saying that you define this parameter tau and minimize tau instead. So here, the epsilon hat and the v hat are still related to the Dirichlet form and the variance, except these are matrix forms of them. So then, OK, the next thing we have to do is think about these matrix forms of the Dirichlet form and the variance. And what we had to do is embed the Dirichlet form into the variance. So how we did that is we utilized this matrix decomposition shown here. We defined this, but we found these A and B matrices. And then these define a matrix W for you. It's not trivial how to find the W, and I will in a minute talk about that. But after you have this W, you take the operator norm of W, and minimizing that gives you the tau you were looking for, where once again, if you have tau, that's essentially 1 over the spectral gap, which is essentially 1 over the mixing time. So then how to find a matrix W like that? What we did there is use something called the canonical path method, or rather a quantum version of that. So for classical processes, it's well known. Essentially, if you have a classical Markov process, you have states. Between these states, you have a link if there is a jump between these states. And so you can think of all these processes, some graph, and there's this whole interesting underlying geometrical picture here. And then, of course, it's a quantum setting, so we had to generalize that to quantum systems, which Kristan did in this paper. And so if you have these, if you have the quantum canonical paths method, then you can easily find the W matrix you were looking for. And so with that, this is essentially the high-level steps of the proof. And I go on to conclusions and some open questions. So what we did is we were thinking about self-correction in general. Specifically, we were thinking about commuting Pauli Hamiltonians and Abelian quantum doubles. And so for both of these models, we derived an upper bound for the mixing time, which is in this form very much resembling the Arrhenius law, which is, I guess, a good thing. An interesting point here is that one of our motivations was looking at entropic protection, and there was this suggestion by Ben Brown that there might be, essentially in his idea, they were looking at an Abelian quantum double structure, and they introduced these defect lines I mentioned here, which the exact construction is not very important. What's important is that even if you introduce these defect lines, our bounds are valid. So we derive the bounds that, so even with the defect lines, our bounds are valid. And if you remember, I also told you that the energy barrier is a constant for these Abelian quantum doubles. So that means that you essentially have a constant upper bound for the mixing time that doesn't allow for self-correction. So the result could be interpreted as an entropic enhancement of memory time, but it's not full self-correction that one would look for. So another thing I should mention is, all right, so if there's no scaling energy barrier, then there could be no self-correction for these models. But it doesn't necessarily go the other way around in the sense that if there's a scaling energy barrier here, that doesn't necessarily mean that you have self-correction. Scaling energy barrier just means that you have a huge upper bound there, which could allow for a huge memory time, but it may not. So it doesn't give us such a strong statement in that case. And so some open questions which our result doesn't apply to, you could, in principle, think about introducing any different type of defects. There are examples of those. We were just looking at this specific type of defects, but you could have entropic protection with other types. You could apply a different noise model. The noise model we used was well motivated in the sense that it's kind of the gold standard for thermalization, but you might think about a different one, and then you might arrive to a different result. And also, there are a lot of models that are not included in our analysis. One of these models are, for example, the non-Abelian quantum doubles, which could be more interesting and maybe harder to attack. So with that, I'd like to thank you for your attention, and that's all.
OK, we have time for questions. Are there questions for Anna? Anyone? Oh, great. Sergey?
Do you expect that memory time of the logical qubit would be smaller than its mixing time?
I'm sorry, I didn't quite hear you. That the memory time of?
So you talked about the mixing time. And we can ask how long time does it take for the logical qubit? How long time does it take before we are not able to report the logical qubit derive?
OK, so I probably should have placed more emphasis on this. So if your mixing time is upper bound is my small value, the mixing time upper bounds the memory time. So if the mixing time is small, then your memory time must be lower than that. I hope that answers your question.
Any other questions? Oh, great. John.
Maybe I missed. Can you comment why you had to specifically work on the ZN models?
Why I had to split that from the Pauli stabilizer setting, or?
Why did you have to distinguish non-Abelian case versus Abelian case?
I'm sorry, I still don't hear you.
Why did you have to consider specifically for Zn doubles?
Okay, so one of the motivations was because there was a suggestion for entropic protection with these specific Zn models. I wonder if your question is about whether we could just simply incorporate the whole analysis for Zn into the first analysis of the Pauli stabilizers. If that's the question, then the answer to that is there are some subtleties that are different in each of those cases. So after you go through the Pauli stabilizer analysis, you can also go through the Abelian quantum double analysis. I guess after you went through the Abelian quantum doubles, you have your toric code result immediately. That's true. But then we specifically looked at the two-dimensional Abelian quantum doubles. So the Pauli stabilizer result is more general because it could incorporate like the Hamiltonian there allows for more opportunity. It's not so strict as the Abelian quantum double Hamiltonian. That's the answer.
Andrew?
I have a question. So has anybody looked at the scheme where the code is changing as a function of time so that you have entropy from that effect? Like through various code deformation procedures, perhaps you can get some sort of entropic protection because the information doesn't know which code it's in.
Yeah, so we haven't looked at that. We just took our Hamiltonians for granted. They are not changing with time, so I cannot really, I don't know what you have there. Maybe that's a good other opportunity to look at, yes.
And I have one question. Along different noise models, do you have an intuition for what noise models might?
So actually, I don't quite have one because I think the reason we used this Davies generator Abelian is because, like, in my mind, this is almost the only thermalization model that really drives you towards the Gibbs state and have all the right properties. I might not know about something, but that's the reason why we use it. But you could come up with something, maybe.
Any other questions? Okay, if not, let's thank Anna again. So now we have a coffee break. Again, coffee.